semantic analysis, and then we'll continue with that particular part of what we call it as the shift reduce parsers. Okay, yeah. Semantic analysis is the next part after your parser. The first phase is lexical analyzer, second phase is our parsers or syntax analyzers. The third phase is our semantic analyzer. So what the semantic analyzer does, how it works, that's what we shall discuss in the consecutive classes, and followed by intermediate code generation as well as code optimization. So things we will to discuss. Fine. To start with, where are we now? This is the objective to static semantic analysis, and we are not talking about anything regarding to this dynamic semantic analysis. We'll mainly two things we will discuss here. Bottom up evaluation, there is a attributed evaluation, and top down evaluation, which we call it as L attributed evaluation. These are the two major things what we are going to learn from this chapter. We shall see the objective in a clear, specific manner. Right. Yeah, this is what is important. Where are we now? In the compiler phases, where are we? So we took the source program, given it to the lexical analyzer. Lexical analyzer scanned the source program character by character, grouped a set of characters by using principle of longest match. It recognizes the tokens, and that tokens are given to the next phase. That is your parser. Parser grouped a set of characters, grouped a set of tokens, constructed the syntax, not parsed. So we are here now. So we have the parsed, means to say we have syntactically correct structure, means to say structurally correct structures. We don't know about the meaning, right? The given structures or the program contains structurally valid program. What do you call it? Structurally valid program. Now it has to be checked for the meaning correctness. So we are here. We have got the parsed. So this will be given to the semantic actions or semantic analysis. What will be going to get? We're going to get an abstract situation. But actually, we'll be getting many outputs of this semantic analyzer. So somewhere it is told that we're going to get annotated parse tree. Somewhere it is told we're going to have the syntax tree itself, or we're going to get abstract syntax tree. Actually, we are not bothered about the output of our semantic action. The validation is important in the semantic analyzer. Whether the syntactically correct structure given by the syntax tree, that is given by the parser, is it meaningfully also correct or not? That's what is the only thing we are bothered. Because the output of this phase will be immediately taken by the intermediate code generator so as to convert it into an intermediate code. So that's the thing. That's the thing. It is written here, IR, means intermediate representation. It is no more a source program, or it is not a target, but it is an intermediate representation. That will be the output of our semantic analysis. So what validation we should do is, it should clearly tell me whether the syntactically correct structure is meaningfully correct or not. So why semantic analyzer is needed? Yes, of course, we need to check the meaning correctness of our program. That's the reason why we need. Have a look at this. While parsing, the syntactical correctness of the program is checked. Yes, that's done. The level of correctness is not captured. There is a level of correctness that is not captured by the grammar. Means our context-free grammar cannot check the meaning correct. So how is the variable declared or not? Variable we have used. So your syntax analyzer checks, yes, ID is a variable. Yes, whether it is declared or not earlier to use, we don't know, right? This is not checked by your syntax analyzer. Or the types are consistent in the expression. I have written C is equal to A plus B. Whether C, A, B, all of them are of same type, or does it need a type conversion, or it has been typecasted. These details has to be checked. Similarly, I'm somewhere I have written something like x is equal to y. So if x and y both are a variable, single variables, fine, that is correct. But if x is float, y is integer, obviously there is a type mismatch. Either of one need to be converted. Fine, that's also fine. But if x is a array and y is a variable, then also it is difficult, or x is a array, y is also an array, then it is meaningfully incorrect. Similarly, we have some other cases. Okay, x may be the name of a function, or y may be the pointer. This and all will lead to structural correctness, but meaning incorrectness. So these all need to be checked during the semantic analysis. Does the method call in the sense a function, is it having a right return type, a right number of parameters, and the right type of parameters? For example, I have a function1, which should return an integer. Right, return type of the function is integer, and it should have three variables or three parameters. One is int, one is float, one is character. But if we have three parameters, one is int, one is float, one is character, but they have written in the reverse order, first character, then integer, then float, then obviously syntactically it is correct, meaningfully incorrect, right? In a selector p.q, right, we'll use this with the structures, something like student dot name, right? If q is not a member, or method field of class p, something like that. If q is not a member or q, then obviously it is meaningfully incorrect. Is variable x guaranteed to be initialized before it is used? These are all few examples that we are looking. But if you go on seeing the meaning incorrectness, we're going to get a lot of such things. That's the reason why we need to do semantic analysis. Your parser or the syntax analyzer just checks the syntax correctness, but meaning correctness is checked by the semantic analysis. But now the question is, how you do all these things? How you check all the meaning incorrectness and clear them, or inform the programmer that there is a meaning incorrectness? Many of what you call editors or IDEs will hint while we are typing the program itself. Correct or not? Syntax errors also they are going to detect immediately, and even the meaning incorrectness also they will detect immediately and will going to hint us. So how that is done? So what is it exactly? Semantic analysis. We just have a look at it. What is semantic actions? While parsing, yeah. Semantic action include symbol table, and that is maintaining information about the user-defined names, maintaining information about the types, maintaining scopes. Second one is context checking, that is scoping rules, type checking. Third one is invocation of code generation routines that is done at the end of semantic analysis. So this is what exactly we need to understand and discuss. Please have a look. We shall go to the previous slide. In all these meaning incorrectness, whether a variable is declared, type consistent, x can be assigned to y, or is there a right number of parameters, and is right return type on b.q is a valid one, or etc. etc. Many such examples, if you look at it, if we clearly look at these things, we can understand one. And I told you that during lexical analysis, any programming language will have 5 types of tokens. First one, let me think, your keywords, okay, which are predefined meaning, which is different. The compilers, you cannot add or remove any keyword. Okay, next we have operators, which are also predefined meaning, which cannot be added and removed. The third one, which is mission defined, operators, keywords, and punctuation. These three are all predefined. They are defined by the compiler. They have specific meaning. We cannot change that. But only 2 types of tokens, that is your variables and constants, are user defined. So in lexical analyzer, we also understood the user defined symbols will going to be entered into the symbol table along with their attributes. Correct or not? And if you look at all these mistakes of our semantic errors, or because of, not because of operators, not because of punctuation marks, not also because of operators. They are because of user-defined symbols, either variables or constants. So with variables and constants, what mismatch is happening? Probable mismatches is, one is type mismatch. The participating operands are of different types. Operands again user-defined. Type mismatch. Second problem is scope mismatch. Some variable may be a local scope, may be used in a global scope, or something belong to a class, or something belong to a class which is used by other one, like this. So all the semantic errors are due to only two reasons, that is scope and type. These two can happen only with user-defined symbol. So for that reason, we need to maintain the symbol table properly. We should get the attributes from the symbol table, attach these attributes to all the user-defined symbols, and evaluate type and scope rules. If they are evaluated properly, then your syntactically correct structure is also semantically correct. If the type and scope rules are not evaluated properly, then it is a syntactically correct structure, but meaningfully or semantically it is incorrect. So this is the only takeaway from this chapter. Very simple thing. The semantic analyzer retrieves the attributes of all the user-defined symbols from the symbol table, which is populated during the lexical analysis, and it is going to be the scope rules and the type rules are verified or checked or evaluated. So if you get the proper evaluation, then it is semantically correct. If it is not properly evaluated, then it is a semantic error. Got it? That's what we try to do. Okay. Yeah. When it will be done? So the significant point, it is nowhere it is clearly told that it is when the semantic analysis need to be done. It is usually done after our what you call syntax analysis, or along with the syntax analysis. Typically, when production is reduced in bottom-up parser, or at a convenient point in a top-down parser, means because your top-down parser builds the syntax tree starting from start state to the string, but your bottom-up parser builds your parse tree starting from string to the start state. So that's the reason. Okay. Okay. Semantic actions that can be performed during parsing also not much important, right? Okay. This semantic analysis is also known as static semantic analysis because it is done just while your syntax analysis or immediately after your syntax analysis. Okay. Now the question is how? We do have only two methods, or these two methods together we call it as SDD, syntax directed definitions. SDD means syntax directed definition. So it's a extension of context-free grammar. In each grammar symbol has an associated set of attributes. That's what I told. Your semantic analyzer should retrieve the attributes from your symbol table attached to all the grammar symbols. That means all the user-defined symbols, and evaluate the characters. Right? Okay. Associate with a programming language construct by attaching the attributes to the grammar symbols. All these grammar symbols are your context, whatever the symbols you see in your context-free grammars. And this attribute are evaluated by using a semantic. What is the semantic rules? Say for every production in your context-free grammar, what it means is specified by the semantic rules. This we cannot call it as a grammar rules. The grammar just specifies which non-terminal is producing which production. The semantic rules tells that what it means. Right? We shall see with the example rather than theory. Okay. There is a thing, a node in a grammar is a record or a field in a holding the information. We shall see with the example. Okay. Yeah. Each non-terminal will have a set of attributes that there may be one attribute or there may be many. That's also true. But the example of attributes, the attributes can be a name, or it may be type, or it may be memory location or address, it may be font size, etc., etc. But usual attributes will going to be type, because we need to check for the type mismatch, and we should also check for the scope mismatch. So usual attribute will going to be value, or it is going to be type. So sometimes we have inherited attributes and synthesized attributes. We shall look at that as we go. Okay. And this evaluation of the attributes will be done by using semantic groups. Okay. Yeah. We do have attributes of two types. S attributes, which we call it as synthesized attributes. Here, the attribute, please understand this very carefully. Synthesized attribute, S attribute, or bottom-up evaluation is when it happens, or how it happens, when the attribute value of a parent node is dependent on the attribute value of the child. Means attribute value of parent is computed by attribute value of child. Then we call it as synthesized. Something like this. E is producing E plus num or none. So you can see here, E is producing, yeah, on the top right corner, you just have a look. E is producing E plus num, right? Now, E2 is the parent, E1 is a child. Now, the attribute value of parent, that is your E2, if it is computed by E1 and num, then we call it as synthesized attribute. Just as simple as that. You can see that we have the attribute val, E1.val plus num.val is giving the value of E2. This sort of evaluation, we call it as what? Synthesized attribute evaluation, or this type of attributes, we call it as S attributed, where if the attribute value of parent is computed by the attribute value of children. Right. Okay. It is used in extensively in LR parsing practice, etc., etc. So the syntax directed definition is known as S attributed definition. And one more thing I need to tell you. Yeah, I'll tell you a bit later. Just see the L attribute. Second type of attributes are inherited attributes. They are also called by the name L attribute. What is L attributed? With S attributed, I told attribute value of parent node is computed by the child. But here, if the attribute value of the child is computed by the parent, reverse order. There in S attributed, it is from bottom towards the top. But if it is in the L attributed, it is top to bottom. If the attribute value is computed from parent to child, or from left sibling to the right sibling, then it is called as inherited attribute. Either it should be computed from top to bottom, or it should be computed from left to right. Left to right. Then we call it as L attributed or inherited attribute. Just have a look at this. D dot type is an attribute, means dot beside the symbol, whatever we write, dot, and the name is an attribute. Okay. T is also having type, L is also having type, D is also having type. Means D dot type is an instance of the attribute T. Similarly, D dot type is an instance of the attribute type. Okay. Now here D dot type is producing T dot type and L dot type. So and T dot type is determining the type of L. So that means you can see here. Now L dot type, if it is determining its child, L dot type, then we call it as this is L attribute. See, it is happening from, in the first example, it is happening from left towards the right. In the second example, it is happening from parents towards the child. This we call it as inherited attribute or L attributed derivation. Okay. At this point, I need to mention one more. Synthesized or S attributed will be pure S attributed. Means in S attributed, all attributes will be evaluated from bottom towards the top. Okay. But in L attributed, Some attributes are evaluated from top to bottom. Some attributes are evaluated from left sibling to the right sibling. And even some more attributes are evaluated from child towards the parent. So L attributed is not pure L attributed, but S attributed can be pure S attributed. Means in L attributed, some attributes will be evaluated from parent to child, some may be from left to right, some may be from child to parent. But now you may ask me that how to evaluate. This is not a written rule, but as a rule of thumb for solving the problem, the way to approach the problem without knowing whether it is a attributed or attributed is, we'll be having the grammar, we'll be having the semantic rules, try to evaluate the attributes from child towards the parent. If you are able to do that, then do it. It is pure as attributed. No need to worry. We try to evaluate the attributes from child towards the parent. At some point, we are not able to move further, then we should stop there and should start from the parent. If from parent we are able to evaluate, fine, good. If not, try to evaluate it from left sibling to the right sibling. This is all. Try with child towards the parent, not possible. Try with parent towards the child, not possible. Try with left sibling towards the right sibling. Got it? So that's how the L attributed evaluation happens. We shall see the examples. That will be better. Semantic rules. What the semantic rules tells is, define the value of an attribute associated with a grammar. Right? Associated with the grammar symbol is used as a node. This is what we call it as semantic rules. Yeah, here we have two parts of our what we call table. One part is telling our grammar rule. The second part is telling the semantic rules, which is going to tell how the attribute values of each one is evaluated. Yeah, have a look at this. L produces here. I'll go from the bottom. Yeah. See the bottommost contextual grammar is F produces digit. Then F dot val is equal to, means F dot val is computed by using digit dot lexval. What is this digit dot lexval? The value that is written from the lexical. I think in your Lex program, the app program, you have seen a token is written, a value is written, correct? No? That's what we call it as lexval. So digit dot lexval, whatever the value that is written by your lexical analyzer, we are calling it as lexval. So means to say the parent, that is F's attribute, that is val, is computed by digits lexval, whatever the value given by the lexical. Similarly, if I have the production F produces open parenthesis, E close parenthesis, then F dot val is equal to E dot val, means the child computes the attribute value of the parent. Similarly, T produces F, T dot val is equal to F dot val. Have a look at this. T produces T1 dot T1 star. Now you may ask me that is what is this 1, what is this 2 and all. So as we grow in the hierarchy, the parent is considered as instance 0, child is considered as instance 1. If at all it has its own child, then it is going to be considered as 2. So that's why we have written in superscripting. Okay, we are writing it to the base of. Means T produces T1 star F, means T0, that is your parent, T1 is a child, F single instance, so again it's a F, something like that. So T dot val is computed by T1 dot val multiplied with F dot val. Similarly, we can make up. These are the semantic rules. E produces T dot val is T dot val, something like that. E plus T, right? All these things. So here the val is nothing but the value that is written by the lexical analyzer. Okay, we shall move forward. So the definition of the simple desk calculator is an S attributed definition, because we have seen all the parent values are computed by the attribute values of the child. Okay, and one more important thing I need to tell you is concerned with your examination. This is usually asked the question from your question paper. Simple desk calculator. will not be given this part also, semantic rule part also. It is, you need to assume and write it. It's as simple as that. When E produces E plus T, it is obvious that E dot val is equal to E1 val plus T dot val, something like that. So you can see the first production, L produces En. We have added a one more star step, L. L is producing E. L dot val is equal to, when you reach this start step, then print E dot val, whatever the E dot val you have, that is going to be printed. That means it is telling a semantic action. It is telling you a semantic action. Okay. Yeah. Now let's see to evaluate this particular value, 3 into 5 plus 4, using this particular semantic analysis. So how to solve this sort of problem is, we are still don't know whether it is a set attribute. We just assume that yes, it is a set attribute, but don't go with the assumption. We are not bothered whether it is a set attributed or a attribute. We try to evaluate starting from the bottom. If yes, fine. If not, we start from again top. If not, we start from left sibling towards the right sibling. Right. When this sort of problem is asked to be solved, the first thing to be done is just to derive the parse tree or write the parse tree by using your production. Using your production, construct the parse tree for the given string. The given string here is 3 into 5 plus 4. Obviously, I can derive this particular string from this particular grammar, correct? And remember to have the associativity and the precedence while you are constructing the parse tree. Okay. So accordingly, we need to start from L. L is producing E. E is producing E plus T. Obviously, we don't have other option. Now this E is producing T. T is producing T star F. So precedence is maintained. So star highest precedence is sent towards the leaf, and plus least precedence is towards the root. Fine. Now T is producing F. F is producing digit. Similarly, here F is producing digit. Again, here T is producing F is producing digit. Fine. So we constructed. Now the first digit is 3, the second digit is here 5, and the third digit is here, what do you call, 4. Fine. Then how exactly to compute? This is just a derivation of a string from the grammar, which we know very well. Now that's not the thing. We need to go for a semantic analysis or S attributed derivation. S attributed derivation. Right. So yeah, have a look at this quick. So this is our semantic. So if you look at it for E or T or F or all these, or even particular, we have val is the attribute. Now the next thing is attach the value. So digit dot lex val is whatever the value that is written from your lexical. Here it is 3. So because of that, and F is producing digit. So for that reason, F dot val is equal to 3 in this case. Yeah. T is producing F. So T dot val is equal to F dot val. So T dot val is equal to 3. Yeah. Here F is producing digit. So F dot val is equal to, again, yeah, F dot val is 5. Yeah. Next, T dot val is equal to 15, because T is producing T1 into F, that is 3 into 5 is becoming 50. Okay. T dot val is equal to 50 because he is producing T. 1, 2, 3, third rule you can see. So accordingly, this is computed. So here digit dot lex val is equal to 4. Here F dot val. And again, he produces F. So T dot val is equal to 4. Now E is producing E1 plus T. In that sense, E dot val is equal to 90. Finally, and L, we need to print the E dot val. So this is an attributed example. We'll stop here. Next class we shall see the L attributed derivation and some more examples. Fine. Thank you. Thank you for joining.